I just want to recall and I write the two basic assumptions that we made. Remember that we have a family of expectation values. These expectation values are defined on an algebra with values in a normed space. And we are doing the following assumption, that En satisfies the singleton condition. Now you know what it is. And that there is boundedness of the mixed moments, which means that the norm of the sequence S1 sigma 1 B Sk sigma k, this norm is in this space with respect to C, is less or equal than a constant that depends only on S1 Sk. These are the only assumptions that we need. And now let us see what will be our implication. So I want to give you an idea of the proof. Remember, the proof has three statements. The first statement has to do with the case in which you have that alpha is strictly greater than 1/2. And it says, let us call, in order not to rewrite every time, we will call the main object of our study, which is the normalized sum of this form, Sn S1 of B. Sorry, the S1 is in B. S1, B S1, Sn of B Sk. We will call the moment of order n corresponding to the choice of indices S1 Sk. So what we want to prove, so this is by definition, this is a definition. So remember, by definition of the expectation value, this is an element of the normed space C. So what we want to prove is this, that if alpha is strictly greater than 1/2, then this moment is norm, the norm of this moment is lesser or equal than this constant dominating the moments times another constant which depends only on k, and the important factor is that here we have some exponent which is exactly k alpha minus 1/2. So when alpha has this, we have this domination, and obviously this will go to 0 because this doesn't depend on, and this doesn't depend on n, and then go n. The n is the cardinality of the finite set, will go to infinity. So it is clear that in this case everything will go to 0. Okay? So, how to explain why it goes to 0? There are some, I will help myself because some formula are very long, so I don't want to rewrite them. So what, however, is important to remember is that each Sn is a sum. You know that by our definition, this sum Sn of B of some Sj was, by definition, a sum over all it is a sum of the B Sj and sigma belongs to n. Remember, n is a finite subset of something, of a given set, the index set. You can think in the classical standard central limit theorem is simply the natural integers. And then you can have, in fact, any subset, any set, any graph. So remember, so each Sn, but here we have a product of Sn. Therefore, our sums, these sums are equal to the following sums. The sum over all functions from 1 k with values in n, and here now I have brought outside the sums using distributivity, so here only the B remains, so I have the expectation of the B. Now, my first main point today is to explain to you what is the role of the singleton condition. So, remember, if there is a singleton in this, remember what is a singleton. I have this map from 1k to n, 1k to a subset n. Then I have an element in the range of this map. And I say that sigma is a singleton if and only if the cardinality of the inverse image of sigma bar, is 1. So there is only one point in here that will have as image sigma bar. One must be, because by assumption, sigma bar is in the range. So this means singleton. And you should imagine k is a fixed, but n becomes huge. Okay? So you think from a moment intuitively. Suppose that you throw, and you choose at random some function sigma. Since you have a lot of possibilities since n, the cardinality of n is much larger than k, most functions will have singletons. So if we use the singleton condition that for all functions sigma which have a singleton, this is identically 0, this means that the cardinality of this sum will be drastically reduced. That is our philosophy. That is the independence philosophy. Independence philosophy means that a priori, you have a lot of terms in this. How many are the terms in this sum? You see, they are as many as the functions from 1k to n. And how many these functions are? The cardinality of n to the power k. But here I have only alpha k. Okay? So you understand that if I want convergence, I must, and I want a uniform estimate, I must reduce the cardinality. Okay. And let me now, so we have said that the non-singleton gives 0 contributions to the sum. So let us try to estimate how many, before this, let me write in more intuitive form this sum. So I will now split all the functions according to the cardinality of the range. So the cardinality of the range, what can be? Maximum can be k, because the domain is k, has k points, okay? So the cardinality can be maximum k. So I will redefine this sum equal to 1 over the cardinality. This is just a factor that remains the same. And then I split over p, which goes, well, this is a function, so the minimum cardinality is 1. Because at least 1 point, the constant, this corresponds to a constant sigma. So, and the maximum is k, corresponds to an injective sigma. And then I will take the sum over all sigma. I will not repeat that sigma is a function from 1k, I hope you remember, such that the cardinality of the range of sigma is exactly p. And then here I have the same expectation. Now the crucial remark that I found first in the paper of von Waldenfels, which is the following. It's a very simple point. Which are the allowed p? A priori, p can be from 1 to k. But we know that if there is a singleton, this term gives 0 contribution to the sum. Okay? So we know that since the union of sigma minus 1 of sigma bar, when sigma bar runs over all elements in the range of sigma, what is this? Of course, this is a partition. It's a partition according to, is a partition of what? Of the set of the domain of this function. I take the range, I take the inverse image of everybody, every element, so this is exactly 1k. Okay? Just by definition of function. It's clear? So, since this is a partition, because a function cannot have two values, only one valued, then we have the very elementary result, that the cardinality of this set, which is k, is equal to the sum of the cardinality of each term of the partition. Now, let me make the assumption. You see, I am summing over all sigma such that the range is exactly p. So let us fix p. So the range of sigma is the cardinality of the range of sigma is exactly p. Therefore, how many are these possible values? We can numerate them, and they go from 1 to p. So it's clear what my notation. If the cardinality has range P, the cardinality of the range is P, then this means that, to say that the cardinality of the range of P means that the range of sigma is some S1 S bar P, and J different from K means that sigma bar J different sigma bar K. This is just definition, okay? So now I have a sum of P terms. Now I put my fundamental assumption on the singleton. The singleton gives 0 contribution, so I neglect. If there are no singleton, what is the minimum cardinality of each of this set of the partition? Huh? What is the minimum cardinality if there are no singleton? Correct, 2. This means that this is greater or equal than 2, okay? But I have P terms. So this sum is greater or equal than 2P. But this sum is K. So it means that K over 2 is greater or equal than P. But P is an integer. It's a cardinality, so it's an integer. So this is equivalent to say, because K can be even or odd, and if K over 2 is greater than an integer, it means that the integer part of K over 2 is greater or equal than P. You see? This is very simple calculation, but this is the fundamental, deep reason why Gaussianity emerges. Because it means that the sum that give contribution, the sigma that give non-zero contribution to this sum are not all possible, corresponding to all possible P from 1 to K, but only from 1 to K over 2 integer part. And now you understand why there is a balance between 1 over 2 and alpha. Okay? You know that by the uniform boundedness assumption on the sorry, this is the uniform boundedness assumption, okay? I use a better notation here because it's very similar. I hope you will not be confused. Okay, this is a number, and this is an element of the algebra. Maybe it's not so good the notation. Okay, an element of the normed space. Yeah, you can distinguish, but I myself had a moment of when I compared this two. But now I think it's clear. So you see, these expectations are bounded uniformly. So the order of magnitude of this sum is not n to the power k, but n to the power k over 2. So that's very important. Okay, why it is important? Now I think I will run a little bit, because you see, once you have this this element, so let us now suppose that we have let us consider the norm of this element, okay? So I want to show, what is my goal now? I want to show that if alpha is strictly greater than 1/2, we will have this estimate. In fact, we will have this estimate, okay? And for alpha greater than 1/2, this will go to 0, okay? But this estimate is now very easy because of the uniform boundedness of the moment. Because look at this expression. I have, if I take the modulus of this expression, in this notation, let me use this notation, if I take the norm of Mn S1 Sk, then I have the norm of this sum. I majorize the norm of this sum by the sum of the norms using triangular inequality. Then this depends only on S1 Sk, so it goes outside the sum. And then it remains how many terms there are in this sum. Well, the partitions of how many functions I can take which have a range equal to p. I can choose the range as any subset of p. I will give you very roughly, but well, maybe here you should see a little bit in more detail. I have written in all the details, but I want to arrive to the independencies. So I want to rush a little bit on this point, which is more technical, but is technical of combinatorial nature. So if you read carefully the proof, okay, what we are now discussing, we want to make an estimate of this cardinality. We fix P, and for each P, we want to estimate how many sigma, which are functions, how many sigma, which are functions from 1k to n, that exist of range exactly P. I will give you a rough idea for this estimate, and then you can complete a combinatorial argument by yourself. Okay, how many choices shall I do? We must count. So we must see the choices. So we have the set 1 to k. And then we have this big set n. Okay? So the first choice I have to do is I have to fix the range. How many I know that the cardinality of the range is P. So I have to choose P elements out of this. And this is the first combinatorial factor that I have, okay? But this is not finished, because once I have chosen the argument, I must decide which k will go to this argument, to this point here. Now, suppose I have fixed one function, which covers all the p points here. How many other possibilities I have? I have p factorial. Okay? So this is another factor, which is p factorial. Because these are sets. I can permute. Once I have a function, I can obtain another function by permuting the range in all possible way. Okay? And now the most delicate point. How many choice I have of this? How many choice I have? I must decide how many elements for each of them will go into the same element in capital N. This is also a combinatorics. How can I solve this problem? This problem is solved relatively easy. I have k elements, okay? So the first, I know that the sum of these cardinalities must be equal to P. So I have each subset here as a counter image here. And I have to fix the cardinality of this counter image. It's clear, this argument. I want to count the cardinality of each set sigma minus 1 as J. This is not fixed when I fix the range, because I have to decide how many points goes into the same point. Okay? So the let me call Sj the cardinality of this. For a single point here, I call Sj the cardinality of this. So what will be the connection between among the Sj? Of course, the sum of all Sj must be equal to K. Huh? Sorry, P, because I have only P values. Okay, I have only P values. Sj is the number of points in the domain that will go to the same value in the range. So, of course, this must be obtained. And they are natural integers, so greater or equal than 0. So, how many independent choices? If I fix the first as P minus 1, the other one is uniquely determined by K minus a P. So, how many choices I have? For the first choice, I have K over S1. Then I have made the first choice. So how many elements remain in the domain? K minus 1, K minus S1. Okay? And now I choose, from these elements, I choose the range of the elements that will go into sigma bar 2. How many I can choose? I will have S2 such elements. And so I will have K minus S1 minus S2. And so on. And at the last, I will have K minus S1 minus, etc., SP minus 1, and then K minus S1, etc., SP, minus SP. So these are the possibilities. Now you do some simple calculation. I wrote, I don't want to write on the blackboard, to see. So this is the partition I, so the set of all possible functions which range of cardinality P will be written in the following way. A single function sigma is completely specified by 3 choices. First, I have to specify the range. How many? Choose a subset of cardinality P here. And this corresponds to this combinatorial factor. Okay? This. The second is I can permute the value. I have P factorial. And the third is this factor. So I can write this as this union. And therefore, we have already calculated the first 2 cardinality we have calculated. The third one, I can do, for a fixed choice of S1, Sk, I have this choice, and therefore I have to sum over all possible solutions of this equation in integers, and I obtain this. You see? But now you see, these elements is such that the denominator here is the numerator here. So they simplify telescopically. And then what you get is this. K factorial, where you see here I have used the fact that the last one is, if I subtract this, I obtain exactly SP. K minus the sum of over Sj from J1 to P minus 1 is SP by definition. But now I use combinatorial identity that I have P to the K means 1 plus 1 plus 1 P times, and this is the multinomial expansion. So this factor is just p to the k. And we calculated this cardinality, exactly. Okay? This is the cardinality of all these partitions. So now we can do the estimate. Now we can do the estimate because we are now, we want to weight this number with this cardinality. That is why we have computed this cardinality, okay? We have to put something here to take care of the cardinality, and you also to remember, sorry, this is alpha. No, alpha was there. Oh, sorry, this was k, was correct. So we have to remember that everything is divided by the cardinality of n to the power alpha k. So we need now something here to weight, which is this cardinality of this sum. And the cardinality of this sum we have computed. We have computed the cardinality of this sum, which is this one. You see, we have, remember, we have three choices here. We have the choice of the subset of the range as a subset, the permutation of the values, and the cardinality of the partitions. But we know, have estimated each of these three. This is as p factorial in the denominator. So this p factorial goes away, okay? And this has, we have estimated that this is exactly of the order of p to the power k, which is this cardinality, the cardinality of the set of partitions, and we have estimated the n. So the important factor is this, the relevant factor, because it's the only one depending on n. And n is the quantity that will go to infinity, okay? So this fact, now we develop the combinatorial coefficient, and we obtain this product. And it's very well known that this product is less than n to the power p, because you see you have a product from 0 to p minus 1 of things which are of order p. Of p things which are of order n minus 1 over n, or k over n, with k is bounded by p. Okay? So this is the estimate that we have. Therefore, the factor that was missing here was a constant times, depending on k, times the cardinality of n to the power p. And now, how does it come, the 1/2? The 1/2 comes because, remember, we know that p is less than the integer part of k to the 1/2. So we have that k to the 1/2, k divided by 2, k alpha minus p. Since p is less than this quantity, this will be greater than this quantity. And this is precisely k alpha minus 1/2. And you get the combinatorial factor. Okay? So you understand? See, we are now in the situation in which alpha is greater than 1/2. So we saw that if alpha is strictly greater than 1/2, all this will go to 0. And we can restrict our attention to alpha equal 1/2. Okay? What does it mean, alpha equal 1/2? It means that k for the alpha is equal 1/2. Let us see what happens. We have that not only that k over 2, so if alpha is 1/2, this k alpha, if alpha is 1/2, this k alpha becomes k over 2 minus p. And we have seen by this von Waldenfels argument that the integer part is greater than p, greater or equal. Therefore, if alpha is odd, k over 2 is strictly greater than, in fact, is 1/2 plus the integer part. And so this will go to 0 like 1/2, like cardinality of n to power 1/2. So we have ruled out odd. Only k even remains. Okay? What happens in k even? In k even means k is equal to, let me write it here, k is equal to 2n, even. Otherwise, we have now proved that everything will go to 0. If k is even, we have that k is even, and we have proved also that alpha is 1/2. Okay? And so we have this p to the, we have p over this. But the maximum of p is k over 2, so the maximum of p is n. Alpha is equal 1/2, k is equal to n, so alpha k is n. So the maximum of p will be n, and they erase. So this estimate now, this factor will be erased by, you see, when you have exactly n. So this proves that there is no convergence to 0. But we don't yet prove any convergence. Okay?
So is it uniformly bounded?
Yes. We have proved that this is in norm. But of course, this doesn't tell us much about convergence. Okay? However, we have proved what we have proved. Let us summarize what we did. We want to find the limit as n go to infinity. And we have proved that only the k even, alpha equal 1/2, and the range, p must be the maximum. So the range of k even and the range of the cardinality of the range of sigma must be exactly the maximum in this inequality, the saturation of this inequality. But k is equal to n, and this equality is saturated for p equal n. So n. K is equal to n and p equal n. So what does it mean that the range of cardinality n and the k is to n? It means that for each sigma bar in the range, of sigma, the cardinality of the inverse image of sigma bar is exactly 2. This is why pair partition exists, come out. Because this means that the family of all sigma minus the counter images of the range, they are a partition, of course, of the set 1 over k, 1 up to k. And each of them, each element of the partition has cardinality 2. These are the famous pair partitions. Okay? I will leave the Gaussian bound because it's very late and I want to arrive to the fundamental point. And I want to try to show you how the... So I give you only the final result that we will be interested in. There are other estimates. This is...
Same thing, the difference also.
huh?
Take the difference and then again you estimate.
No, what is the result that we obtain? Ah, sorry. I have to change a little bit. One moment, just a moment.
So some of this question.
This one. This is the other lecture, the one. Okay. So this is what has been our result. We have shown that this limit is equal to this. In what sense? In the strong sense that this limit exists if and only if this other limit exists. And in this case, they are equal. Okay? So this is what we have proved. We have reduced the problem. Now, I just want to mention, because you are interested in asymptotic independence, what here we do exactly with the singleton. In asymptotic independence, you do by splitting. And you have, of course, to work much more with estimates, because you have to show that this every singleton is not exactly 0, but almost 0. Okay? And this is the, but conceptually, when you understand independence, dependence is a technical improvement, but it is easily handled. So now this is what we have proved. Let me now remember this formula, and let me try to very quickly explain why entangled ergodic theorem comes in. I will very quickly explain. I will not give you the detail, but the details are also all written. So well, some of these things we could have used, but okay. Now, look at this formula. In this formula, I have the sum over all the pair partitions of this K. We know that K must be even. I will rush a little bit. We will come back on this point, but I want to show you the real essence of the matter. Okay, I want what would be the goal of my point? I give you a definition. So I give you the definition of what does it mean entangled ergodic theorem. So I say that in the standard notation that we have already used, So the B Sn are as before. This family of operators satisfies the entangled ergodic theorem if the following limit exists in norm in the C space. What is the particularity of the limit? You see, in the von Waldenfels theorem, we have lemma. We have reduced everything to pair partition. Notice that here we have exactly the pair partition structure. Sigma 1 is exactly one index equal to sigma 1. Sigma 2 is exactly one index equal to sigma p, to sigma 2. And the same, sigma p is exactly one index. So we call entangled ergodic theorem because, first of all, what it has to do with ergodic theorem? Well, to understand what it has to do with ergodic theorem, suppose that when the sigma, you are in a boson type situation. The boson type situation corresponding to tensor independence is when, for different sigma, you have commutation. So the B corresponding to different sigma commute. So if you are in this boson type situation, since the only sigma equal to sigma 1 is the first one, I can commute this sigma here wherever it is and bring near to this. And I can do this for everyone. So what I will receive in the end? In the commutative case, remember, I have this sum. This sum is exactly cardinality of n to the power p factor. And here I have exactly p pairs. If everything commutes, I can bring everything here together. And I reproduce the standard ergodic averages. You see? So why entanglement? What is entangled? Exactly. I give you a very simple example. For p equal 2, when you have p equal 2, it means that you have 1 over cardinality of n over to the power 2. Then I have only summation over 2 indices. And then I have the expectation n of b sigma left 1, s left 1 sigma 1 times the non-trivial situation. Here we will be discussing the difference between, you will understand the why from central limit theorem ergodic crossing and non-crossing partitions play a different role. Let us see in the case of 4. We have B. Here you have the left. You want to know where the other sigma 1 is. So you have 4 possibilities, 1, 2, 3, and 4. So you see that you have 2 possibilities. The sigma 1 and the sigma 1 is just after sigma, is just on the right of this. And the other possibility will be this. Okay? There is a third possibility, which is for us also interesting, which is this. 1 with the 3 and 2 with 4. This is the famous crossing partition. I rewrite it here. Because if I have 1 with 3 and 2 with 4, I have a crossing. That is why, that is the difference between crossing and non-crossing partitions, okay? Now, in our case, suppose we have let us consider the most interesting case that I will call here crossing and totally entangled is the same thing. So let us consider this case, the crossing one. So the index will be, here will be sigma 2 with some index which necessarily will be a left. Left 2. And necessarily this, well, because we are in this situation, this must be sigma 1. And this will be another possibly different, S of R1. And this will be necessarily sigma 2 with F of R2. The upper indices correspond to the component of the vector, remember. So they can also be equal, I don't care. The only important point is that the lower indices are equal. So this corresponds to the non-crossing partition. I want to explain now why, look, and you see now, if the algebra is non-commutative, you cannot, this is not a standard ergodic theorem, because non-commutativity brings you something new. You see? So the first person who tried to give proved, but he had some very strong assumptions on the operators. Essentially, I think, if I remember well, they were compact operators. Okay? And there was Liebscher. And then after Liebscher, Fidaleo worked on this entangled ergodic theorem. And many people, he says, Field Medal also worked. I don't know very much because I didn't follow the literature after. But it's very interesting that this entangled ergodic theorem, as you have seen, they come naturally when you study central limit theorems. Okay? Now, let me show you another thing very important, which is the necessity to go beyond the singleton to say something interesting. And so, again, I will illustrate only in the case of a four point. And then you generalize. The notes are for the general case. So if I have 4 points, you remember the singleton condition means that this thing is equal to 0. Let me simply write huh?
The way you wrote on the product form, this goes out.
Well, commutativity will play with product form commutativity. Of course, you can say the ordered product. But so singleton means that this is equal to 0 if some index sigma j is different from all others. Okay? Now, I want to say, suppose that there is one sigma j, let me call it sigma j0, different from all others. What is a strict singleton? Strict singleton means that this is equal to E of B sigma j0 times E and the expectation of the other three in the product. Okay? There is a very simple counterexample. Of course, if the algebra is an identity, or in fact, if the elements on a different sigma belong to algebra with the same identity, the two are equivalent. But it is easy to construct examples in which the two are not equivalent. And it is a fact that most, in fact, almost all independence notion satisfy this, but extremely few satisfy this. Okay? Essentially, Very, very, very few independence notions satisfy strict singlet. Huh?
Having unity in the algebra
Is important. Is important. I have written here a very simple counterexample, but time is short, so you can read in the lectures the counterexample with 2 by 2 matrices. This is done with 2 by 2 matrices. But now what I want to explain is what happens, why there is a big difference between crossing and non-crossing. You see, now I suppose a strict singleton. And suppose we are in the non-crossing situation. Let me take the simplest non-crossing situation. Simplest is this one, 1, 2, 3, 4. Simplest non-crossing is this. Okay? So simplest non-crossing means that I have to change this index. This is 1, 2, this is 3, 4. So this means 1 is equal to 2. So I must put 1 here. So this becomes R1. And I must put 2 here, and this becomes L1, L2. Okay? B sigma 2. Now what happens? Now you see, if I group these 2 elements, they are all in the algebra A sigma 1, because the product of 2 elements of an algebra is in the algebra. Now I use a strict singleton, and this will factorize, and will become equal to 1 over cardinality of n, sum En over sigma 1, in n, of B sigma left 1, sigma 1, B S right 1, sigma 1, times the same thing with the 2 instead of 1. Okay? So now you see what happens. If you have strict singleton condition, when you have a simple situation like this, but let us see the other non-crossing partition. What will happen with the other non-crossing partition? The other non-crossing partition is that will be 1, 4, and 2, 3. Okay? So what will be the case 1, 4, 2, 3? This product will be like this. E, B sigma 1, B sigma 2, I omit the superscript, B sigma 2. But here I have again sigma 2 because I am in this situation. Huh? So, and B sigma 1. But this is in the algebra, and this is a singleton. So using a strict singleton condition, I bring out, again factorize. I bring out sigma 2. Again factorize. Okay? But suppose now you are in the previous situation, the totally entangled one. The totally entangled one means I have E, B sigma 1, B sigma 2, B sigma 1, B sigma 2. And sigma 1 is different from sigma 2. What is the simplest condition that would guarantee to me? I have already shown that under strict singleton, and if I have non-crossing pair partitions, everything factorized. So the limit is reduced to the limit of this single.
So use the commutation relation.
No. We arrive to commutation. But what is even simpler than commutation? That for every totally entangled partition, this is identically 0. This is the definition of free independence.
Oh, that's the free independence.
That's free independence. You see? So the free independence,
It means the one you cannot calculate, you put 0.
0. You see? In fact, under strict singleton, and in free independence there is strict singleton, if you see, this is a slightly generalization of free independence, because it is so-called pair partition free independence. Because I am asking only for pair partitions. But free independence asks even more. But even if the partitions are not pair, the same is true for totally entangled, okay? But for central limit theorem, it is sufficient, this weaker form of free independence.
So this is the starting point of Spiker's observation?
No. This is our paper with Obata and Hashimoto.
That is a different.
Yeah. This idea that it is entangled.
Spiker?
No. Voiculescu arrives to free independence in a completely different way from the free group.
But Spiker arrived free independence?
Spiker uses the definition of Voiculescu. But we are doing here a more subtle thing. We are deducing the notion of free independence from the central limit. This was never done. Yeah. You see? We are deducing the natural definition of free independence. What is free independence? It's the simplest condition that guarantees existence of the limit. Yeah, because you see, you understand that this argument generalized to any 2n.
Q commutation is also one of
Q commutation will come. We will come later with the. Of course. So you see, you disentangle. This is the philosophy. That is why central limit.
the motivation of all this commutation relation. You can say we want to do central limit.
Right. They are sufficient conditions for disentanglement, for the validity of entangled ergodic theorem. Of course, the entangled ergodic theorem is very interested.
In case of boson, this issue is trivial. I can see.
Huh?
These issues are quite trivial. In case of bosonic case, the one it's not really
What? No. The estimates are the same.
No, I'm saying is actually the you can say it's multiplicative, some kind of ergodic theorem, right?
No, but this is in the tensor case, this is just a standard ergodic. The non-commutative ergodic theorem for polynomials.
Yes.
These are the mixed moments, so they are non-commutative polynomials, and this is just a standard non-commutative ergodic theorem. But I call this entangled because it's much more than non-commutative. This is much more. You cannot reduce entangled ergodic theorem to non-commutative ergodic theorem. It's deeper. And of course, that is why it's more difficult to prove.
I should study no central limit theorem.
Huh?
I should also study no
So the theorem that I want to emphasize to you to close this lecture is that the theorem that we have proved, not proved, but essentially given this definition, there is the following theorem. If there is a strict singleton, and if this essentially the covariance exists, because we know it's a necessary condition. This is a necessary for central limit theorem. So if the necessary condition exists and strict singleton is true, then the central limit theorem is equivalent to the entangled ergodic theorem. Equivalent. If and only if.
But your concept or your limiting condition on CLT is quite strong compared to the classical one. With the norm and the
This is a moment.
convergence. So
This is what, for example, nobody has gone beyond this in quantum probability, except
not in terms of factor,
except the Verbeer school, and myself and Bach. But
the Verbeer school is looking at exponential.
Verbeer school is very special case because Weber theory is only tensor independence.
That's why I
It is, in fact, not. It is a tensor framework. The difficulty of their results comes because we have not independence, but a kind of asymptotic independence. Right. So their weakening goes in the language in the direction of asymptotic, not of in the direction of more complex algebraic structure. For example, in their case,
So
the entangled ergodic theorem is completely trivial.
So your covariance term CBST, that one you.
It's the limit of this.
You are not assuming any algebraic property like for example non-negativity or there's nothing.
No.
Assumption.
No, no. It's not a true covariance. It's not a true covariance. It's just a what in physics they call two-point function.
Yeah, two-point correlation.
Yeah. Well, in fact, not even correlation, because you speak of correlation when you have a state of positivity. Yeah. But here, just a completely, just a map. Just a map. Okay, I think we can finish. Thank you.